This is our last tutorial. Josh and Francis are going to teach us about multimodal transformers. Go ahead, guys.
Are we presenting with the microphone?
Yeah, I can pass it to you.
That would help.
Thank you.
I can speak up if needed, but okay.
Speak up.
Can everyone hear me? Okay, perfect. So as Solomon mentioned, we'll be covering the last tutorial of the morning before going into lunch and the talk in the afternoon. And we're taking that topic of transformers that was covered at the end of tutorial 2 and moving into this idea of multimodal transformers that has, in the last couple of years, been, I think, probably one of the biggest shifts in focus in the transformer kind of field. Me and Francis will be covering it. My name is Josh. I'm a recent PhD graduate, or I recently got my PhD at UMaine. I was one of the earlier members of Salome's lab. Francis, I'm going to introduce yourself.
Yeah, I'm a recent graduate here at SDSU. I started at the Sekeh lab last fall, and yeah, excited about multimodal transformers.
Okay, so let's get into it. And when we're talking about multimodality, you can think a little bit about it from a biological perspective with humans, where we have, a number of different senses. And you can think about how they help contribute information about the world around you. Think, for instance, if you're trying to decide whether or not some food has gone off, you have, smell, you can visually inspect it. If you try and taste it, like you can taste maybe a sour or bitter taste. And these different modalities, these different types of data input can help you contribute to a better overall kind of holistic understanding about the situation, come to a better conclusion about how you should respond to it. In a similar way, multimodality in neural networks is aiming to do that same thing. So we can consider some problems like with medical diagnostics. You might have visual data, such as scans of a patient, and those can typically give you some information that can help with making a diagnosis. But it would be beneficial if you also had something like text data of the patient's medical history, and that could contextualize that visual image in a more kind of nuanced way for that individual patient. So this is one kind of example of how multimodal inputs in a network can take into account both this visual data and this text data to make a more well-reasoned conclusion, essentially. You can also think about something like the field of autonomous vehicles, autonomous navigation, which has been an area of significant interest since, deep neural networks have kind of come about. And in particular here, often these autonomous vehicles will have something like a visual camera, as well as things like spatial sensors like LiDAR. And similar to with the medical diagnostics, those will of course contribute some kind of information in different modalities that can work in a complementary manner to give a more holistic understanding of the area around the vehicle. But you might also have situations such as like fog or inclement weather, where maybe the vision data is kind of corrupted or impeded in some way, and you can use that spatial sensor to help compensate for that kind of loss of understanding of the scene around it. So not only can it help make a more kind of well-informed decision, but it might also add some level there of kind of robustness to loss of functionality of various modalities. Now, having kind of introduced this idea of multimodality here, I want to give a little bit of an overview of what we'll actually be talking about in this tutorial. The first one is kind of covering some of the history from what was covered in tutorial 2 up until modern day, seeing like what has been the focus of particularly like large companies with their proprietary models over the years. And then giving an exercise where we just look at how you can actually implement some of those LLMs yourself, as well as just comparing kind of the behavior outputs of them across different kind of generations and seeing how they've improved. From there, we'll be kind of shifting into the core of the tutorial, looking at multimodal models and giving an exercise, looking in particular at one of the more often used vision language models. Lastly, we'll be recapping kind of what we covered and giving some future directions at how the field is kind of moving forward with this idea of multimodality. So for this kind of history, I want to look at a vertical slice, particularly of the GPT models, because they were one of the kind of early adopters of transformers. And they've pretty consistently had some cutting edge models, each of the, I would say, like generations of LLM improvements. And this is going back to when that first transformer model was made in 2017, just to give some context of like the timeline we're working with here. And to reiterate some of the stuff from tutorial 2, kind of the core introduction of this idea of transformers was that query key and vector, and value matrices, and the multi-head attention mechanism or layer that is the hallmark of the transformer. Now, just 1 year after that first paper, I believe OpenAI put out this first GPT paper for GPT-1 in 2018, where the focus was on task agnostic LLMs. So being able to have an LLM that can work with this kind of tokenization system and prompt in different ways to handle a variety of downstream tasks. It was trained on 7,000 unpublished books, which is, I think, probably sounds like a lot of data for now, but it's going to get larger, as you can imagine. And the model had about 120 million parameters. So if you think back to tutorial 2 with like ResNet, that was also in the millions of parameters. So it's not like a crazy number quite yet. But if we go just 1 year later, 2019, they came out with GPT-2, where now the focus is on handling this zero-shot kind of transfer to new tasks. So if you train it on one setting, it should then be able to handle other settings without kind of having to be given examples of that new setting. And you can think about this with like ChatGPT. Often you can ask it to do things like, oh, give me a response in a certain style, or write me lyrics in the style of this particular artist or something. These are kind of tasks it wasn't necessarily trained for, but it can kind of directly be transferred over to. And I mentioned we had 7,000 books in the GPT-1 training data. Now we have 40 gigabytes of data, 8 million documents. And the number of parameters has increased over 10 times to 1.5 billion. Just 1 year after GPT-2, we have GPT-3. If I'm remembering right, I think it, beyond just being a year, it was a number of months where this paper was put out for GPT-3, showing that they were able to significantly increase the size of the network and the training data to improve its performance, improve this zero-shot ability of the network. And when I say they significantly increased the size of the data in the network, they increased the size of the network over 100 times to 175 billion parameters. And the size of the training set from 40 gigabytes of data to 45 terabytes of data. And, I believe this is the model that they use for open, like the ChatGPT website when it kind of started really taking off. So this is probably one of the earlier models you are familiar with if you were engaged with that. And you're probably aware that even back then, there were some kind of issues with the outputs, things like overconfidence with some of its answers. You can often kind of prompt it something and it will just take it at face value and be like, oh yeah, that thing you asked me, that's definitely true. Another kind of known issue was due to the size of the network, there are kind of inference costs on their end in terms of the energy consumption, in terms of the actual financial aspect of running it. But all things told, it was a significant improvement over GPT-2 in terms of utility. Now, looking to recent years, we have GPT-4, and to avoid just focusing on OpenAI, there are of course also these competing models like Google has Gemini. In this most recent year, Meta put out Llama 4. There's DeepSeek, and all these newer models, they are still kind of continuing that trend for the most part, where we see GPT having a relatively small number of parameters, and over time just the significant increase in parameters from generation to generation. So there are some models like DeepSeek, for instance, that was kind of looking at reducing that issue, trying to make it more efficient. But in particular, with this most recent generation of models like GPT-4, Llama 4, one of the biggest focuses has been adding in that multimodal functionality. For instance, with GPT-4, the ability to provide it images or ask it to generate images through text prompts, ask it to describe the images that you pass in, for instance. So that is going to be what we're talking about for the later half of this tutorial. But for now, I want to give a brief exercise where we're just looking over comparing some of these generations of LLMs and showing you how you can interact with them through Python. 1 second to going. Okay, so for the sake of time, because I didn't want to be loading in models while this is going, because some of them take a little bit longer for the more recent ones, I have already loaded in these Hugging Face models the same way that Mary did in tutorial 2. And we're going to start off by looking at...
Just wait a little bit, please.
Oh, yeah.
Just wait. Yeah, thank you.
We're going to start off by looking at GPT-2, which was gotten from Hugging Face through this community group for OpenAI. And I have a number of different questions that I have asked it through this simple function. And all this function is doing is passing in some string, placing it into this format of prompt template of Q question and then A, and it's prompting it for an answer. And then that prompt is tokenized and passed into the model. We're decoding the output and printing that output to the terminal. So for example, if we take this first question where we are saying, okay, we like Breaking Bad, we like Band of Brothers, do you have any other shows you might recommend? And you can see that it's answering here, no, I don't have any suggestions. So it's actually giving us kind of a reasonable response here. But it's saying, I'm always looking for new shows that are more interesting, and then it gets cut off. And the reason it's getting cut off here, just to point out, is that this function here has a max token length. So it's allowed some number of tokens to respond with, and then we're terminating that sequence and just printing out what is the result. And you might be familiar with, like, again, using things like ChatGPT or Gemini, where typically they'll end on a more kind of organic note. They won't just stop mid-sentence. And that's typically because there are other mechanisms in place that will ensure that there's some kind of reasonable interpretation or organic kind of semantics at how its response is formatted given the token constraint. So it's kind of working around that rather than giving a response without knowing the constraint and then just getting truncated at some point. So I just wanted to point that out so you're kind of aware of that if you're using these out of the box like LLMs. Now, just looking at some other queries or some other prompts to get a sense of the behavior of GPT-2. We're asking, I'm a programmer, Python's my favorite language. Do you have any recommendations for other languages? Don't have much information off of this one because it's just saying Python is awesome. It is. But the next one can give you an example of like these earlier models sometimes had some odd responses like how to learn fast. And to be fair, it's a bit of a brief question, but it says, I try to learn fast to be able to stay away from my opponents. My opponents are really fast and I'm just trying to be able to stay away from them. And I think it's cut off here, yeah, to be able to. And it's just like a little bit of a silly response. It doesn't tell us how to learn fast. So it's kind of, you can kind of see the underpinnings of similarity and attention. It's probably associating speed fast with running away from someone rather than really focusing on the learning aspect. So there is still some like logic behind it in terms of there's similarity between the response and the question, but it's not really understanding what we were asking for. Another common issue we can see with the next one, I love basketball. Do you have any recommendations that for sports I might like? And it just keeps repeating, I love basketball. And that I think, especially with the earlier generations of models, is something that came up, which is it would like fall into loops. It would kind of come up with a low loss output and it would just keep saying that until the tokens ran out. Similarly, how to get rich. I'm working for a big company, but not looking for a big paycheck. I'm looking for a way to make it all worthwhile. Then there's some kind of issue with the output here where it kind of starts generating a new question. But it's getting at this same idea of like, there is a similarity in the idea that we're asking of, you know, wealth and companies and paychecks, but it's not really answering the question. Now, moving from those individual prompts, I wanted to get in another point for people who have used commercial LLMs, which is the idea of like memory of the chat. And here we have a simple while loop that's just going through a back and forth Q&A, asking a prompt, having it return something. And I just ask, you know, is the sky blue? Yes, it is. It doesn't really have some knowledge base that it's referencing to check that, but it probably has a strong similarity between sky and blue. So it's probably in some way showing off of that to give an answer, yes. It sees like, oh, you asked a truthful statement or something with a high similarity, like what it or high attention, then it's probably true. Again, then it had GPT-2 had this odd behavior where it would generate its own Q&As. So I'm going to skip over that for a little bit. But asking it, you know, what was the previous question I asked you? And it goes off on some unrelated thing. It doesn't really recognize the question I asked it. And this is to point out that it only sees the prompt I'm currently giving it, whereas I believe a lot of commercial LLMs will kind of in some way include some portion of the recent chat in memory or in the prompt when getting an output so that it has it in the context of that larger conversation. So I mostly just include this so that when you're using these out-of-the-box LLMs from Hugging Face, you just kind of know what to expect, what you might need to work around. But the last thing I wanted to do here for this exercise is comparing two different generations of the Llama model. Both of them are kind of more competent, I believe more recent than GPT-2. And they are 7 billion and 8 billion parameters respectively, or sorry, it's a typo, Llama 2 and Llama 3. We had to swap it from Llama 4 because Llama 4 is actually so large that you can't load it into Google Colab even on an A100 setup. So if you want to use Llama 4, you can actually do it through the dataset card on the Hugging Face model. There's a little window for inference where you can provide inputs and see how it responds. But for the sake of this workshop, for this tutorial, we're doing 2 and 3. And once again, we're setting up this answer generation prompting function. And we're going to ask each of those two models the same question. I love basketball. Do you have any recommendations for other sports? And we're going to ask it for 3 different like token allowances just to see how that affects the runtime needed for generating a response for both models. And for the largest amount of tokens, we're going to compare the responses that it gives. So we see here, when we just ask it for 50 tokens, it takes about 15 seconds for it to generate for Llama 2, and it takes about 18 seconds for it to respond for Llama 3. So again, it's 7 versus 8 billion parameters, so it's a fairly proportional difference in the runtime. But now when we go up to 200 tokens, we're asking it to make 4 times as many tokens. It's about 86 seconds for Llama 2, and about 95 for Llama 3. So it's significantly slower here to generate more tokens. Another thing that's a big factor is this, the sequence length, like how many tokens are in your input that it needs to kind of do attention between. I believe it's quadratic scaling for the attention heads, because if you have, 10 tokens, it needs to do attention, between 10 tokens with all of the other 10 token or 9 tokens. But if you have 100, then it needs to do 100 tokens, getting attention with all the other tokens once again. Now moving to this largest test, we have 500 tokens. And again, the runtime goes up. We have 225 versus 257. But now I want to focus on the actual outputs it's giving, because you can see that they're a lot more reasonable than GPT-2 was. Even by Llama 2, we already had pretty polished responses. But if we compare the answers it gives, I want to point out kind of something that I've noticed over recent years, especially with these more corporate models, where the response for Llama 2 is, if you love basketball, you might also enjoy other team sports that involve similar skills and strategies. And it gives some recommendations. The syntax is reasonable, the choices are reasonable. But looking at Llama 3's answer, it says, that's great. If you enjoy basketball, you might also like other fast-paced, high-scoring team sports. And this highlights one thing I really want to point out, which is this kind of shift to a more organic or natural kind of response, where it's giving some kind of, pleasantry in its response, saying, oh, that's great. It's complimenting the question. You'll probably see this all the time working with a lot of the more recent models, where if you ask it a question, the first thing it's going to do is compliment your question. But it also is giving more specific examples of what it's comparing or why you might like these things. They're fast-paced, they're high-scoring. It's not just that they're similar, it's kind of trying to actually report some of its, the things that it's finding similarities in, presumably. So going from GPT-2 up to that, we've already gone from having these really broken, repeating responses to these well laid out, responses with correct syntax, where it's kind of trying to begin to actually be a bit more personable or, act more like a human in terms of how it is formatting the response. Okay, so that leaves off the exercise 1. We are now going to shift gears into this multimodal learning. And as just a reminder, this is this idea of having multiple types of inputs or multiple types of data being either input or output from the model. And in particular, we're going to focus on these 2 questions of why are we using transformers for this multimodal learning? And how can different types of data actually be compatible and used within the transformer? And we can think back to the figure that was given in tutorial 2 for this kind of original transformer, where we have some key features such as the tokenization of the inputs, the embedding of those tokens into some embedding space, and the multi-attention head that is kind of the highlight of the transformer architecture. If we think to the multimodal setting, this is a relatively more kind of advanced multimodal architecture put out from Facebook, where it's looking at a multitask setting. And you can see on the right side here, one of the tokens is the task, or one of the inputs is the task index itself for what task you're working with. And then on the left, we have the image inputs and the text inputs. So we would need to do some kind of a tokenization for each of these modalities. We would then need to embed them into some embedding space, including like adding that positional embedding. And then have some way to get attention between modalities. And you can see here in this example, they're taking the outputs of the image and the text encoders and they're concatenating those responses. So they're basically combining those responses and they're getting the attention between that result and the task index modality. And so the question is, why can you do that? Why can you get attention between these different modalities? And well, why and how? And the how part is pretty simple. It's pretty straightforward. If we think back to the multi-attention head or multi-head attention, we have the values, we have the keys, and we have the queries. And here, some of those are coming from one modality and the rest are coming from the other modality. So we're making comparisons essentially between the embedded data for the visual images and for the text inputs. But that kind of begs the question, why are we able to do that? Why is this data compatible in the first place if one of it was images and the other was text? Why can we get attention between them through this kind of dot product approach? And Francis will be covering in the following slides how we can do that through the embedding and through the tokenization. Take it from there.
Yeah, thank you. So yeah, tokenization and embedding is the process of how we take these different inputs into our models and make it into a way that the machine can understand. And this is very important when we're thinking about multimodal models, because we have to be able to convert all these different types of inputs, text, images, videos, as we saw before, into a shared space that makes sense. So as was covered by Mary and Aditi in tutorial 2, tokenization is a process of taking the actual input into and turning that into like a numerical value. So we have it here where these are different strings, or this is one long string that's been split up into different tokens and then converted into a number. It's a token ID. And the number is sort of arbitrary. That process is different for each model. Then that token gets converted or embedded, that's the verb that we use, into a vector. And that vector is stuff that we can plug into the model, do math to get some form of output depending on the specific task of your model. So again, in multimodal AI models, what we're going to be doing is taking in different things that aren't text. So in large language models, obviously we're using text as a form of input, but we also have to consider if we're inputting images, documents, audio, pretty much anything, we have to be able to convert that into numbers, which then can be embedded into vectors or matrices, any dimensional ND array, so that we can do some mathematical functions to it. So what's important about the tokenization process and embedding is making sure that they are aligned together and that they're in the same space. So here, this is an example of just using text, just for simplicity's sake. On the top right, we have the actual sentence to date. The cleverest thinker of all time was. That gets converted and embedded into a series of vectors for each specific token, right? It's important that all these tokens are comparable with each other, right? So that we can do some math and make some assumptions. So these two vectors, bound and jump, because they both have similar meanings, the vectors are going to be pretty similar to each other. It's when we're doing multimodal AI like models and stuff, we have to also make sure that different inputs also have like shared similarities. So for example, if I have an image of a red apple and I tokenize that and convert it into a vector and I embed that to a vector, that vector, just like how bound and jump are very similar, should be very similar to the text input of a red apple, because they should be easily comparable with each other and, be plugged into the AI model. So now we're going to go over like the different inputs and like how they get tokenized with each other, or how they get tokenized. This is again language. This is covered in tutorial 1, but it's the process of breaking down like the actual phrase into those tokens. Those are the tokens, not the embedded vectors, again, because they're just one number. As was covered again in tutorial 1 was also this process of doing it in images. So in images, what we do is we split it up, and those are called patches, and then we convert those patches into tokens. It's important to remember that when we do this, we split it up into different patches. We can lay them in a flat line, this is a linear projection, and we have to also maintain their position. So we have to know that this is in the top left corner, and like the other stuff are in the different corners, and that's part of the positional embedding that was also covered in tutorial 1. Once you have those tokens and they're embedded, you can just feed them into your transformer model and then do whatever process that you want to get your specific task. So for example, in this model, it goes into an MLP head, and then it's a classifier. So it takes the image and tells you what is that image showing you. So one example of another form of mode is audio. So you can actually take spectrograms or waveforms, and you can do the same process where you split it up into certain patches and then perform some mathematical functions that will get a token and then embed that token. Again, it's really important that when we have a multimodal model, which means that it takes in multiple forms of input, the embedded space should be shared. It should be a shared vector space so that they can be easily comparable with each other. This process of embedding the different modes of input is called embedding alignment, which means that in this example, what we have here is we have like the inputs. So we have a model that can take in images, audios, and videos, and it gets tokenized. So it gets split up into parts, and then it gets converted to a token, and then that token gets encoded into a vector. And then in this example, there's a specific dedicated alignment module, which means that you do, again, mathematical functions to get all of those into the same vector space. So there could be a series of like linear projections, transforms, if you guys know linear algebra. And then you get the new embedded tokens, and then that just gets fed directly into the model. And what makes this really cool is that you can really put any sort of input you want into the model, as long as you're able to tokenize it and then project it onto the same vector space. So for exercise 2, we're going to go through using CLIP as a multimodal model, which maybe some of you have heard of. Okay. So what is CLIP? CLIP is a model from OpenAI that tries to identify or match pairs of text and images. So if you imagine a data set of a bunch of different images and captions associated with that images, we can see that here in the bottom right. You can see it's a picture of 2 elephants, and the caption associated with it is a large elephant standing next to a baby elephant. That is like the type of data set that CLIP is trained on, and the goal of it is to be able to like get some or project both the images and the captions onto an embedding space that like makes those like match very well. And it does that through the process of contrastive learning, which we'll be covering and going over. So here we're downloading the data set. We're going to be using conceptual captions when we're running inference, and I'll kind of explain like what is the point of this exercise towards the end. And here is us actually downloading the model. It's important to know that we're using OpenAI's pre-trained weights. So as was discussed in tutorial 2 again, you can download pre-trained weights from Hugging Face. So after a model has been trained over and over and over again, they will save those numerical values after those like epochs of training. That way you don't have to run that training module again. So we're not going to be doing any training, we're just going to be using OpenAI's clip module. And the important thing is the tokenizer. So that's what we're going to be using today, is the actual process of converting those images and text into tokens and then predicting them on the embedding space. So as we discussed above, remember that we have to be able to convert different modes of input onto this and project them onto the same embedding space, and that's the process we're going to do right here. This is we're going to be embedding all of the text in the conceptual captions database that we looked at earlier, and we're going to be doing the same thing for the images here. So let's go over what CLIP actually is and how it's been trained. So CLIP uses something called cosine similarity, which is basically a function that tells us how similar two things are to each other. So if you remember the example I used earlier, where there's an image of a red apple, and you compare that to a text of a red apple, after plugging that into the cosine similarity function, it should yield closer to 1. The range is from -1 to 1, but I believe the math we do here normalizes it from 0 to 1. And then does it in percents. So the process of training CLIP is you feed it a bunch of text pairs that should match to 1, and you go through all of those data, you go through all that data, and you fix the after the cosine similarity, you put it into a loss function, which we'll show later, and it will try and like increase that value to show that like they're closer to each other, and then it'll also give them mismatch pairs. So stuff that should not relate to one another, and those values should be lower down in the cosine similarity. So just to recap, higher cosine similarity values means that the text is closer to each other, and low cosine similarity values means that they're farther apart, they're mismatched. So we're going to be doing an example here. So I took just like a random image from the conceptual captions database, obviously. This is a bus station, and then the caption here is a very typical bus station. So this is a matched pair, right? It's exactly how the caption is exactly how it describes it. And the cosine similarity value is 27%. So it would be 0.27. So you might be wondering, okay, why is it so low? Like why is it like that? Well, that's because it still is, we'll talk about this later, but it's outside of the dataset module. But we're just computing the cosine similarity. So we're not doing any training on it. It hasn't seen this data set, so it doesn't perform as well. But what we're doing here is we're actually just calculating the cosine similarity between these two images and captions and then plotting them together. So when we're actually training CLIP, again, we're not doing that here during this exercise. What we're going to be doing, what that process is called contrastive learning. So it gives it a bunch of match pairs, and it gives it a bunch of mismatch pairs, and it trains the model to align those two together and try to get the model to be better at identifying mismatch pairs and match pairs. And so what we do is we take the cosine similarity value and we put that into a loss function, which is right here. This is one of the loss functions that you can use that we're using when we downloaded this module, and you can't really see it because it's a little small, but this dot product, that's like your cosine, that's like akin to your cosine similarity score. And for loss functions in general, a high loss function means that the model is performing worse, which means that it's mismatched. And a low loss function is that they're correctly identified. And what you want to do is you want to try and get, as we feed it more like information, we want to try and get the loss function lower and lower and lower, as was covered in tutorial 1 and 2. So when we're running inference with CLIP, a big topic that we talk about when we talk about multimodal AI models is zero-shot learning. So the ability for your model to perform well on data that it hasn't seen. This is because like in multimodal models, you don't have access to all the data, especially as things get more complex. There might not be readily available data sets that you can use to train your model. So zero-shot learning, you can think of like if you train the model on an image set of dogs and cats, and like it's a classifier. So is it a dog or is it a cat? or is it a bunch of other stuff? You want it to be able to, after you train the model, let's say give it an image of a lion, it should correctly identify that it's the lion, even though it's outside of its data set. That's kind of the whole idea of zero-shot learning, is like being able to perform well outside the data set. So conceptual captions is not one of the data sets that the CLIP model's been trained on. It's a bit of an older model, actually. It was published, the paper was in 2021. So when we're running inference, we're just using it. That's like something that we want to talk about. It's like how it performs outside of the data set. So what are we going to be doing with this CLIP model? We gave it the entire, not the entire, actually, just a small subset. I think the first 100 or 1,000 images of conceptual captions, and we're going to prompt it in a query. So that's right here. We convert that query into that query text into a token, and then embed that into the vector space using CLIP's tokenization. Then we look through all of the images in the conceptual captions, and those images are going to get tokenized and converted using CLIP's tokenization process into the same embedding space. And we're going to return like the top 4 images based on our query. So yeah, we're going to be calculating the similarities again using the cosine similarity matrix. So it's going to be very simple. And that's this line of code right here. And then it's going to get the top 4 matches. So I'm going to run this, and I'm going to do, let's do a bus station. Let's see what it returns. So these are the top 4 images. It's going to project, or we're also going to show the actual caption. But again, it's important to remember that when we're running this function, we're actually just comparing the vectors of our query, a bus station, and the vectors of the image. And we're going to see how it like compares to the actual caption. So here is like obviously, well, what it should perform well, or like the actual answer, right? Like I'm looking for an image kind of like this. And then some other stuff that kind of gets thrown in the mix. So this is like a museum, public park, and then plants, the jetty. What we can assume is that like there's some features within this image that makes it look like a bus station, or like gets it projected onto the embedding space like a bus station. It could be the fact that it's outside. It could be like the specific architecture of this. It could be like that it's not like the people maybe that gets associated with the bus station. But yeah, these are the top 4, and this code will be available to you guys. You can play with it and query different things. And if you want, at the very top, we only include the first 100 images here. So you can actually include the entire data set. We do that because when you convert, like it takes a long time to process. So we just gave it the first 100 images. But it's really cool. It's a really cool like system. What we can also do is we can do images to images. So we can use, going away from the multimodal model and like showcasing the fact like I don't have to give it a text. I can also like use it as an image to image. We can see like if I give it an image, a query image, what are the images that are associated with it that look the same? And what's cool is like, because we already project everything to the same embedding space, we don't have to do like extra work. The only bit of code here is we have to have an if-else statement, and like being able to convert that image into the tokens and embed that. So that's like the only difference here. So we're using the same function. And what I'm going to be doing is I'm going to be using this image of a tree. But you can kind of get the picture. It's an image of a tree, and what we should be seeing is similar images of trees. So it's a query image, and these are the similar images of trees. And so these are actually comparing the image to the image, but it's using the same process as discussed above. What's cool is like we can take this backbone of CLIP, this process of putting text and images onto the shared embedding space, and use it in multiple different ways. CLIP isn't really used by itself, it's used as a backbone for a lot of other models and a lot of fluff around it. So this is one context called MedClip, where it uses it takes images of like medical data, so like CAT scans, MRIs and stuff like that, lung scans, and puts that into a database. It's a database here. And it also has associated with those scans like descriptions, whatever. Small note, I don't know what this is, but yeah, a description of the actual image, right? And if this looks familiar, it's the same cosine similarity matrix that we had all the way up here. It's the same cosine similarity, so it's using the same mathematical properties as CLIP, but in the medical context, which is really cool. And so that's kind of the power of CLIP, of being able to project into the same shared embedding space, vector space, is that you're able to use it in like very, very unique ways. Let's go back to the presentation. So just to recap, we're hitting the tail end of this workshop, and then we'll break for lunch. But we talked about large language models. We talked about like the advent of the transformer and how quickly it's been able to transform, no pun intended, the large language model like ecosystem. And the important bit is that with transformers, you can have multiple different types of inputs by using the multimodal cross-potential block. And the process of tokenization, embedding, and alignment, that's all how we break down those different types of inputs and then put them into comparable units and numerical values. So what's the future? What's really cool is that because we're able to like, if you're able to take any input and then put that onto the vector space, you can take any input that you want. So this is an example of image line. This is a older model from 2023, I think. It takes the typical images and text and videos, but it can also take depth sensor data, thermal data, and egocentric videos to and then like do some cool stuff with it. This is really cool because now if you think about like sensor data and stuff like that, it's very, very particular. So we don't have to go through the process of converting that into stuff the model knows. Like converting it into text or converting it into like a CSV file, you can actually just feed it directly into the model as long as you're able to tokenize it and then project it onto that embedding space. You don't have to go through that extra work, which is really cool. I believe that's it.
Yeah. Open up to any questions. If anyone has any, either on the LLM stuff earlier or on multimodal models in general. Yep.
Yeah, so you give me an example about I like basketball, and then number 2 and number 3 gives a difference. So number 3 say, hey, great, right? But then the detailed recommendation, which sports that I should get involved, quite different. Which one is better?
I can go back to it real quickly, but I mean,
I understand the first sentence, say, hey, great, you like this, you have some emotions, but then the recommendation are quite different. So I'm not a sports fan, I just wonder.
yeah, I mean, I honestly think that they both give, in terms of like responses, they're both like all team sports. So it's giving, I think, good answers in either case. But I think even in those other like sentences, they have a lot of those points I mentioned where like they're actually giving specific reasons, like high scoring or fast paced. They actually, I will say the same words quite a lot. Like you can see like agility, I think was used here a couple of times. Fast paced, high scoring. Like those were some of the things that they had up here in this first sentence as to what they're recommending us. So I think it has more of that tendency of like finding the similar words maybe and kind of reusing them. Probably in terms of loss, it results in a lower loss. So it finds that like using those particular tokens is better. So I think that the suggestions are good in either case, but I feel like Llama 3 is trying to use more specific language kind of rather than just generally be like, it's similar or it's a team-based game or something. At least it's kind of hard to say with just comparing one response here. But that's the read I get from it.
So because I saw the volleyball and the hockey are quite different. Anyway, thank you.
Other questions? Get to all of them, we have time.
Do the lengths of the embedding vectors ever matter in this case? Because I see the cosine similarity normalizes it by the length of the vector, but are there any like instances where the length of the vector could matter?
That's a good question. I think, obviously if you have a higher length of the vector, like you can include more information in that vector. But what that does also increases the computation time and like the actual computation itself. So it's a bit of a trade-off where you do get more information. But like you do increase computation time. So sometimes like it's not really necessary. But obviously like these large language models, like they're huge and like the number of parameters and like the math that gets done. So when you consider like how much parameters and like the size of those models, like you kind of want to like keep it kind of concise. But like obviously like if you have like insane training, like an insane training system, then like you can really jam as much as you can. Good question.
And I have another question about clip. So how it works is it matches, like given an image or something, it matches like the closest text caption that it has. So it doesn't like generate a new text or anything for it.
No.
So how would it work if you give it like an image it hasn't seen before? How does it choose a caption if maybe there's not a very good caption for it in the word bank that it has? How would that work?
Well, in the exercise, those are images that it's never seen before. So what it does is it takes in like an image and a text and it like computes some score, right? And so like what our exercise is doing is like giving it an image or giving it text. So you can think about the core example, it gives it text and it goes through all the images and it computes that score. So I think to answer your question, let me know if I'm getting it right, but like I think it's not really about like generating a caption, it's more like how does it's about computing the actual score. That's kind of like the whole process.
And just to tack on to that, it also depends a little bit because you showed there are multiple ways to use clip, like image to image, text to image. It does depend a little bit what you're passing in, because like if you're doing inference where you just have a bunch of images and you want to classify the labels, it would get the cosine similarity with all of the known like classes. It would basically say, what are the classes we've seen? What are their names? And you would treat those like captions to match against. But if you give an image, then it's just comparing that image's like embedded representation with all of the images that it can match against. So it's based on that cosine matching kind of, but it depends on what modality you're working with.
Great question.
There's another question here.
With the multimodal models, is that something going towards, looking towards the future, is that going towards like broad AI, or is it still considered like a narrow AI because it's all the image, the text, the audio, all kind of similar? Is this still considered narrow AI, or is this going towards like a broad?
You say broadness is like general AI or like working with different
Like this, like instead of like just a text, image, audio, like combining them all, like more adding more modalities.
Yeah, I think I would say it's probably moving in that direction, but I think it's probably a spectrum. Because like, especially with transformers, there's a lot of emphasis on like zero shot transfer onto new problems, the ability to take something that was trained on one thing. And you know, I think I gave an example earlier with like GPT where it's like, you know, you weren't necessarily trained on Billy Joel songs or something, but like give me something in the style of like Billy Joel. Like it's not necessarily the task it was trained to do, but it knows enough to kind of move to it. And I think the more modalities you add, the more kind of ways it has to do that kind of zero shot adaptation to new settings. So I imagine probably as the scale increases, it's kind of just a spectrum as it moves towards the ability to handle a larger kind of array of problems into something that probably looks more like the broad AI that you're talking about.
Yeah, I think it also referring to like AGI, like artificial general intelligence. I think like that's something researchers who are focused on AGI, like they wanna like make sure that there's, like they're focused also on multimodal AI models, because like for it to be AGI, it has to interact with different modalities and different types of data. So does that answer your question? Oh, yeah.
Just to add on that, one of the talks this afternoon is the modality of video and audio. So then you will kind of see more examples of those two modalities.
Are there any more questions in person? Okay.
So having used like AI quite a bit, I was kind of curious of like, why does it seem like when like these kinds of like text generation models, as they get like better, they also feel a lot more comfortable to almost like filibuster with all their tokens. Like if you look at Llama 2, it's got a very concise ending, right? It says these are some examples and so on. But then on the next one, it like is like, oh, give them a try. Which one do you enjoy the most? Would you like to know any more? Do you have any other questions? I'm here to help. Feel free to ask me anything. I'll do my best to help. Like, why do they filibuster so much?
My understanding is that's a corporate thing, that they want you using their model, so they want you to engage with it with another thing. So like, that's the best reason I've seen, and it's hard to say exactly, because a lot of the models we use are proprietary, like big company models. But it's most likely it is an engagement thing.
Okay.
But also, it also does play into what I was saying earlier about being a bit more human, though. Like, if someone asks you a good question, you're trying to be very like customer servicey kind of, you prompt them like anything else they can help you with, right? If you've ever talked to like a call center or something, like they will ask you that, like, anything else they can help you with. It's like, I think it's probably emulating that a little bit as well, trying to be polite, trying to be helpful. Probably some combination of those factors.
Other questions? Yeah, we have one.
Back here.
Yeah.
Thank you, I got it. Meantime, you guys can check the Q&A.
So I know that image files, for example, it's not just the image itself, but the contents and properties of it, like the metadata. When you feed AI the image, like, and it has the file, does it take a look into the metadata too to try to answer the prompt you give it regarding it?
Yeah, when you say metadata, do you mean like location data, like where the image was shot, and like the files, like that type of stuff?
Yes.
Yeah, so the actual like tokenization process is just converting the JPEG into the image, whether or not within the JPEG file type it stores the metadata, I'm not too sure, but that's definitely, I honestly don't know, and that's something that I'll look into.
Yeah, like per clip, it definitely would just use the pixel values, but I feel like I have read, and it would be based on like different methods might dig into that metadata and try and use it in adding some information. I feel like I've read some cases from papers of like people trying to do that to help add additional information about the images. In that example you're giving, that would probably be like a text input that it would feed into the network alongside the image, like pixel values. Yeah, I think it comes down to different methods, maybe different data sets set up to have the metadata available as text data, or different networks that actually read into it versus other networks might not. Good question though. Is there, I think one just came in on.
One question there.
Yeah.
Okay.
Yeah, could you elaborate on?
I think it was from tutorial too.
Oh, my bad.
Yeah, or on the, just one, new one.
There's only one question, right?
Yeah. The encoding and decoding was from the previous tutorial.
So that one.
How does fine tuning for a specific task work? For example, to have Q&A chatbot versus translation task. That's, I think, kind of tricky to answer, because I think it's getting down to why are transformers so good at zero shot, like or transfer to new tasks. And a lot of it comes down to just the size of the training data, again, like terabytes of training data for GPT-3. My understanding is it largely has to do with the kind of system of tokenization, having some way to represent different words, having a vocabulary basically that the model is able to draw from, rather than, you know, something like CNNs, you're just working with like features that you might detect or something. You have to detect them within the image you're working with. But here we have like a vocabulary that even for like humans, there are, you know, a large number of things we can do with language that are very different. You know, you can write music, poetry, you can do crossword puzzles. Like there's all sorts of different ways to use vocabulary. And so I think that between having a large model that's able to handle tokenization, able to handle drawing like syntax comparisons through like semantic comparisons through the attention mechanism, I think just as that scales up and as you have vocabulary and that tokenization and the shared embedding space we were talking about for multimodal models, it just gives it the tools that are needed to adapt better to different tasks than what it was necessarily trained on. That's at least my best understanding. I don't know if there's anything you have to add to that.
Yeah, I think also like in terms of fine tuning, like that does like a good job of getting again those pre-trained rates that we covered in tutorials you covered. What we can also do is feed it extra data. We did this, I think also in the AI Club, where like we took like a GPT pre-trained model and then we fed it like Canvas discussion board data. So it got good at emulating like Canvas discussion board data. So I think that's kind of also a thing, but I think most of it is what Josh is saying. It's like, it's just like if you just give it a bunch of data and like the models are so large, like the zero trial learning is kind of insane. Do you know if grammar rule is organically learned throughout tuning or is imposed later by NLP techniques?
I think it's a little bit of both. Because I think a lot of like the grammar rules come down to the multi-attention head, right? Like having maybe one head like dedicated to looking at certain dependencies or relations between the sentence. But I think big companies like OpenAI, I think also have a lot of oversight on like some supervision and rewarding or selecting responses that are grammatically correct. Like I know I think it's starting in GPT-4 for OpenAI, they start asking you might have seen this if you use at least ChatGPT, they'll like give you 2 prompts and they'll be like, which of these is better? And that's kind of you doing their work for them and giving them some supervision, probably in helping polish this grammar and stuff like that, and see what feels like a better response to a person.
Yeah, I think it also just comes down to the training data. Like, I don't know if you guys have seen on the internet, but like you can tell if something is AI generated if it has the M dash, like that's usually the telltale sign. But that's just like largely because what we're training it on, even the first GPT model, as Josh mentioned, is like books and like written data, and like authors will use M dashes. So like that's kind of the thought process. But like Josh was saying again, like OpenAI and like these large companies will pick and choose space because this is a consumer facing product usually in terms of large language models. So they wanted to make it personable and stuff.
Yeah, there's a lot of, I think, holdovers from the fact that the people, going back to tutorial 1, these models take a significant amount of money, hardware to run, to train them. And so we're kind of dependent on the larger ones that are available. Even for Clip, I think a lot of the ways people use it is just out of the box, pre-trained. I think with transformers, that tends to be the case. So there's a lot of things that come down to, it's a consumer facing product. The people that are able to afford to train them are consumer facing companies. So you get some artifacts from that.
Great. That's thanks to Josh and Francis. Graduated from that, and he was my first PhD student. Do you want to share your story a little bit with students so they can get inspired by?
Yeah. Anything in particular?
Like you didn't graduate in CS.
So my undergraduate was biochemistry. I went and worked for a few years. I had kind of done some coding up until that point with like C++ and whatnot, and I decided I want to come back and do computer science. I looked for labs that were doing AI, and Salome was one of the few labs at UMaine that was doing some really interesting work. And so a lot of my PhD was working with from continual learning. So the setting where you have like one network and you're training it sequentially on a series of different tasks with the goal of preventing it from forgetting information or worsening its accuracy on the earlier tasks that it learned. Yeah.
How many years?
Uh,
In the lab?
5, I think it was maybe 6 years total, 5 in the PhD program, because I had to do some like undergraduate prerequisites and whatnot. Yeah, it was very interesting. Did some internship with Cisco, and also been able to work with both other kind of fields like material science and other universities like Northeastern on some collaborations. It's been a very interesting time. It was a nice experience.
Just an inspiration, if your background is not CS, you always can change, or if your background is not AI, you can always, if you're interested and persistent, you can continue and learn and get to the level of being an AI expert, right?
Especially for AI, there's a ton of opportunities for cross-disciplinary things. Like my background was biochemistry, so in tutorial 2, they're giving protein folding example. Like that's something I might do in the future. Like working with problems like that. Like there's all sorts of ways to tie in what you've already done into AI because it can be used for anything.
Exactly, and it's been amazing to have him in the lab. Francis, I think since I joined SDSU, you took my neural network class and then computer vision and joined the lab. So he just graduated so he just graduated from CS bachelor degree, but he knows more than that, so much. So it's been great to have him. AI Club, right? And we have a lot to do in the lab, but do you want to say a few words? Your journey, everything.
Yeah, the research that I do is I'm into computer vision, so it's like being able to like give a model an image and like it's kind of wild actually. Like the images with the medical stuff, I did research when I studied abroad there, and it was so insane because if you know the math, like you can apply these computer vision models to like anything. And so the work we do right now is we look at traffic videos and we try to identify the agents on the road, so like cars, pedestrians, trucks. The issue is that we have a lot of cars, and we have a lot of like trucks and buses, but we don't have a lot of pedestrians and bikes. So what we're trying to do is improve the performance in like a class and balance setting. So it's really interesting work. It's a lot of fun.
Multimodalities, I think. So.
Yeah, multimodality, exactly. So highly recommend it. SDSU has like a lot of great resources in terms of like GPU stuff. And if you guys are interested in AI, I have to plug the AI Club. Best club on campus. Number 1.
Okay. Right. So you've done with tutorials and you've been amazing. Patient audiences, thanks for great questions. The next step is to take a break, and it's a lunch break. So my team are going to help you to find your way if you don't know where the third truss is. And then at 1 p.m., we're going to start the afternoon session, which is going to be in the theater, okay, right around the corner. And we are going to have 4 very interesting talks. People are coming from Utah, Texas, above 51, so just stick there and we're gonna enjoy it. All right, have fun and enjoy your lunch.
Right. We're gonna do